Hi, I'm Benjamin, and I'm going to give you an overview of our paper on visual DNA. We started working on this project because we realized that we don't have good tools to compare images in datasets. We often rely on metadata to understand what's different about the datasets, but that doesn't tell the whole story, and really you should be looking at what's in the images specifically to understand their differences. Current dataset comparison approaches are not sensitive to many of the variations that can occur in images. We propose representing images in datasets using distributions of neuron activations. To create them, we pass the images to represent through a pre-trained feature extractor that's frozen and monitor the activation values at each of the neurons. We then fit the distribution, and that creates the DNA representation. This representation is very granular because we have access to different neurons that react to many different things, and it's very compact to save and can be compared with custom distances. We show applications of visual DNA on many different tasks and image domains, from evaluating how realistic fake images are to predicting the transfer learning performance of a semantic segmentation model. We also release a bit package for easy visual DNA creation and comparisons, so feel free to try it yourself. So, let's go into a bit more details. What specifically is a visual DNA? Given a dataset or a single image to represent, we rely on the features learned by a pre-trained, frozen neural network. We found that there were many networks that had good performance, but the self-supervised vision transformers usually did best. What we do is that we take the images to represent, we pass them through the pre-trained feature extractor, and we monitor the activations at each neuron that we've selected that are spread throughout the network. We then fit the distribution to the activations, and we experimented specifically with histograms or Gaussians. Although, when we look at the activations, we did seem to get better fit with histograms. Representing datasets with visual DNAs can be very compact. If we were to save the 70,000 images of the Flickr Faces HQ dataset, it would take about 89.1 GB. If you wanted to keep track of all the raw activations of the feature extractor, that would take you 1.10 terabytes. If instead you use a visual DNA with histograms or Gaussians, you can save a representation of the whole dataset in less than 15 megabytes. Another benefit of visual DNAs is that they don't need that many images to represent a whole dataset. We found that after 400 images, the representation often starts to stabilize, and you don't get much by adding more images. So far, we've talked a lot about creating a DNA, but not really about using them. If you want to compare visual DNAs, you end up actually comparing distributions over all the neurons. So if you use histograms to fit the activations, you can use the Earth mover's distance to compare distributions for one same neuron. If you use Gaussians, you can use the Fréchet distance. Now, what if we want to figure out which neurons are sensitive to an attribute we care about? Well, you can take the DNA based on images that all have that attribute, and another DNA based on images that don't have that attribute. If you compare those two DNAs on a neuron-wise basis, you'll get one distance per neuron. So for example, if they were histograms, you would get the EMD for each neuron, and that will give you one number per neuron. Now, if that number is pretty small, that meant that the distribution of activations between both DNAs were pretty similar, meaning that the attribute, being there or not, did not really change much to what was happening at that neuron. On the other hand, if there's a high distance or high EMD for histograms, then that would mean that the neurons are sensitive to differences in those attributes. And this is a good indication that you found a neuron sensitive to the attribute that you care about. And we can then order, for example, neurons by their sensitivity to attributes. Using such an approach, we could rank neurons by their sensitivity to images of people wearing eyeglasses or wearing hats. In this example, we took the DNA of a reference image and ranked comparison images by how close their DNA was to that reference based only on the top n neurons sensitive to that attribute. It turns out that a single neuron can be enough to match images of people that also wear glasses, and 20 neurons are sufficient to also match people who are wearing hats. Sometimes you just want to compare images or datasets globally and take into account every possible source of differences, in which case you can do a holistic comparison by taking two DNAs you want to compare, comparing them neuron-wise and getting a distance, for example using the Earth mover's distances if you were using the histograms, and then you can combine all those distances you get for each neuron using, for example, the average, which will give you one final distance between two DNAs that is pretty holistic and takes into account all the features that are picked up by all the neurons. However, sometimes you want to have something that's a bit more specific because you care about one specific property of the data. In that case, you can still start by getting a neuron-wise distance, but then you'll have to try to combine the neurons so that they match the attribute you care about. This can be done, for example, by only using neurons sensitive to what you care about, that you have ranked like we did before, or you can optimize for some weights that will combine neurons such that they are focusing on the attributes of interest. This can lead to a weighted distance between the two DNAs that would focus on what you care about. So using these applications, we were able to use visual DNAs for many tasks and covering a wide range of image domains, even though we never had to retrain or tune the feature extractor. This is all with a frozen network. So one of the tasks we looked at is, could we rank fake images by how realistic they were? And we did that by getting the visual DNAs of individual fake images and ranking them by how close those visual DNAs were to a reference DNA of a real dataset of the same domain. And we did that while focusing on neurons that were the most sensitive to realism that we found by comparing a dataset of real images to a dataset of fake images. Another experiment we did was trying to see if we could optimize weights to combine neurons such that we would start being insensitive to selected attributes but still sensitive to the rest. And so we did that on the face dataset where we had 50 label attributes, for example, wearing hats, having straight hair, blonde hair, wearing eyeglasses. And for each one of those attributes, we tried to optimize a set of weights that would make any distance between two DNAs not take into account differences on that attribute, while keeping the sensitivity to all 49 other attributes. And that worked very well. Another task we did is trying to retrieve the most similar images to a reference dataset, and this was done by taking the DNA of the Cityscapes dataset and ranking the DNAs of other images from different datasets by how close they were to that reference. And we got some really interesting looking results that you can check in the paper. Another cool task was trying to predict semantic segmentation transfer learning performance, and this was done by trying to look at how close training and validation data would be in terms of visual DNA and seeing if that correlated with how a model trained on that set and evaluated on that set would perform. And it turns out it's a very good predictor of which training sets will do best on which validation sets, just based on how close the visual DNAs are. And for this one, we specifically used neurons from a very late layer of the network. So that's it for this short overview. Thank you very much for your interest. There's many more details, explanation, and results in the paper, and we're sure there's a lot of other applications and extensions of visual DNAs to explore. So if this is relevant to you, please try it. We made the PIP package to make it easy, and we're looking forward to having some feedback.